Well, for the hardy souls who have taken some time off today to join us, this is our first ever GemQuest meeting, and we have no idea how big or how small it will be today or in the future, but we're hoping that interest from today will grow so that as we move from gem to gem, we will have a growing audience. And it's an outreach to not only students, but people who love gems, and I'm hoping that's a common factor for everybody here. We're all basically, I hope, have a camaraderie of gem loving that goes not just to the technical, but also to the aesthetics and and the art of gems. So the reason for moving today to have our first gem as diamond is that it's rather unique in the world of gems in a number of ways, in that it has amazing properties of electrical and heat conduction, which make it useful in areas far beyond gems. And because it's high Mohs hardness scale hardness of 10, it actually has a great deal of use in a number of other industries, including the oil industry, mining, industry generally, and as an abrasive. So it's something that's unique, but unique in another way, in that it's, I think, the only gem in the gem kingdom that is a one element gem. And someone please correct me if I'm wrong. But unless we're looking at some of the newer soft gems where we have things like sulfur, people are actually faceting sulfur. I don't see that it's going to have much competition in the area of the one and only single element gems. So we gathered together a number of people who have expertise in the field, and we do have at least one person from a museum. I was hoping from some participants from the Smithsonian, and we do have somebody representing the Science Museum in Ottawa. So that's all really positive things for our future. And we had a bit of a rough plan of what areas we wanted to touch in discussion. And I'd like you, if you wouldn't mind, Julian, to sort of screen share for a minute the lineup of what we're hoping to touch on today.
Sure, bear with me a second. So Ray has prepared this wonderful Word document, which I will um, share with you now for a second or two.
There we go. Sorry to blank some of you out there, but so I just wanted to say that during most of the day, the time we're doing this, we're going to ask people to maintain themselves in the mute level unless they're going to be participating. And if you take a look at the overall listing here, I do have some names here that people have been so kind from the GIA to contribute in terms of information in some of the areas I wanted to cover. But that doesn't mean they're the only persons to speak then. So if you have an interesting question that you feel you'd like to have dealt with in any of these areas, please take a note while it's on the screen of what area you would like to ask a specific question about or make a contribution to, and then let us know on the chat side. Aim your chat message to Jolion, and he will sort of keep track of who wants to say or has questions or has things they want to say in the various sections that we want to try and go through. So that's basically the housekeeping part. I do want to, I was kind of surprised to find out when I was initially getting involved in the jewelry trade that there are vast differences across the world in terms of the actual hardness of diamonds. I used to think when I was naively first involved that all diamonds were just hardness 10. But then I found out that the difference between corundum, which is 9, and 10 was a magnitude of almost 100 times harder. And then within the range of diamonds themselves, there's also a fairly wide range of hardness. And I've been told, and please correct me if I'm wrong, that in terms of a cutting situation, one of the hardest diamonds in the world to actually cut are those that come out of Guyana. So I think that's kind of interesting because it never was occurred to me when I first started off that diamonds might be varying in their own hardness, let alone within the same crystal having directional hardness changes as well, which make it quite challenging when they're trying to be polished. So because of the grain and the hardness variations within diamonds, and sometimes the almost invisible, in quotes, knots that cutters run into when they're cutting, make it challenging for people to take a rough and uncut stone and turn it into something that has magnificent refraction and clarity. Anyway, at this point, I'd like to call upon uh, Evan to talk about the different kinds of diamonds that there are out there, and just share with us some of the information he has on that.
Yeah, thank you. So usually when we're talking about types of diamonds, we're talking about the type classification scheme of diamonds, which divides diamonds into two categories based on whether or not they allow ultraviolet rays to pass through them. But we have a better understanding of what that actually means now. Now we sort of talk about type 1 and type 2 in terms of whether or not they have nitrogen in their crystal structure. And that's something we can measure using infrared spectroscopy. So type 1 diamonds are the most common kinds of diamonds, maybe like 98% of the diamonds out there. And in infrared spectroscopy, you can see that they have nitrogen that absorbs some of that IR within a certain region of the spectrum. And there are sort of three different configurations that nitrogen can be in. One, it can be in little isolated substitutional nitrogen atoms. Two, it can be in pairs, and those are called A centers, little pairs of side-by-side substitutional nitrogen atoms. Or you can have an aggregate of two pairs with a vacancy. So you have 4 nitrogen atoms plus a vacancy, and that's called a B center. So those are all different kinds of type 1 diamond containing this nitrogen impurity. The other kind of diamond is type 2, and type 2 diamonds don't have this absorption due to nitrogen in infrared spectroscopy. So they can either be, we sort of break that down into two kinds of type 2. We have 2A that shows no nitrogen, and we don't see absorption due to anything else. And then there's type 2B, where we actually see some additional absorption in infrared due to boron. And those can sometimes be blue in color. And a good example is the Hope diamond. These diamonds are some of the most valuable ones in the world when they're this beautiful blue color. So those are usually what we're talking about in terms of diamond type. But I mean, you can also sort of break diamonds up in lots of other ways, like color or shape or size, or sort of based on their geological paragenesis. We could talk about different types of diamonds. For instance, like geologists, the two types of diamonds that they talk about, and I come from a geological background, so they often talk about P-type and E-type diamonds, peridotitic and eclogitic, based on the mineral inclusions we sometimes find inside. So P-type diamonds look like they grew in peridotite because they have a mineral assemblage that recreate into a peridotite host rock, and eclogitic diamonds look like they grew in eclogite in the lithospheric mantle, so at a depth of maybe 150 to 200 kilometers. That's one of the things that makes diamonds so interesting from a geological perspective, is they actually come from the Earth's mantle as opposed to the crust, like most other gem materials we're familiar with.
Okay, that I know you're getting a little bit technical there for some of us, but I wondered if you could just take that another step and talk about, if you will, since we've got you on screen, a little bit about the main mining locations in the world, because I know we look at two primary sources for diamonds, alluvial and matrix in terms of the pipe locations. Can you just touch on briefly, what I was hoping you might touch on briefly, is the type of diamonds that are coming out of these different mines, and what are the advantages, for example, of alluvial mine source diamonds versus the ones that are found in situ.
Okay, yeah. So maybe that's what you meant by type initially, and I kind of went off on a bit of a rant.
No problem.
But yeah, so when diamond, like I said, diamonds form in the Earth's mantle. So how do they ever get to surface? Well, they come to surface in volcanic eruptions. The most common mantle-sourced volcanic eruption that would contain diamonds is a kimberlite. So it's at surface, it looks like this sort of narrow, almost like a carrot-shaped pipe usually, and that would be like the primary occurrence of diamonds as we find them at surface. And a lot of large-scale diamond mines around the world are mining a kimberlite pipe. But sometimes we see places where a kimberlite has been eroded and all the material has been washed away. And a lot of that volcanic rock is very mafic or ultramafic, so it weathers pretty easily. The material gets shed out into some kind of waterway, and then we have alluvial deposits in either rivers or sometimes along beaches, where the diamonds, because they're relatively dense, they're a density of 3.52 grams per cubic centimeter, they settle with heavy minerals, and they're also very, they're robust physically, so they stand up pretty well in the sort of the tumbling through a river deposit. But deposits like that, there are fewer of them that are mined on a commercial scale. Quite often those are more like artisanal mining operations. But there are examples along the coast of Namibia where there's marine mining. You've got boats out there that have like a big hose and they're sucking up sediments from the sea floor, like from some of the nooks and crannies in the bedrock where the diamonds settle down. And sometimes those are actually really high value diamonds because they're ones that have fewer cracks quite often. They've made it all the way down a river and been, you know, they've survived this washing back and forth along a beach environment. So it's the survivors that make it into that setting.
So basically, what you're saying then, if I hear you correctly, is that the alluvial shoreline diamonds and the river diamonds have actually been banged around enough that their weaknesses and flaws have caused them to already be cleaved and cut down to a rather stable core. And so there's less waste in those diamonds than there would be in diamonds that are mined in situ that might still have internal stresses.
Exactly, yeah.
Yeah, which is actually kind of interesting. And what I was hoping you also would share is some of the major mines in the world. And I know that you've had some experience with some of the new, I don't want to see the pictures of those yet, but I'm hoping we'll see them later.
I was hoping to pull up a map. I can't share content right now. I need to be allowed.
Bear with me a moment.
Jolyon will help you share if you need to.
Hold on. So I've got to find you. Here we go. What I'm going to do is make you the host for the moment. Now you can.
Oh, now I can share stuff. Yeah. Okay. Can everyone see this map?
Yes.
Yeah, so this is a whole map of the world with lots of different deposits shown on it. And in the top right, you can see sort of a breakdown of the major gem diamond producing nations in the world. And if you've never really seen this breakdown before, it's kind of surprising that Russia and Canada make up like half of the world's diamonds. People often kind of have an idea of diamonds coming from Africa. And that's true for parts of history, you know, for parts of, you know, the earlier in the 1900s, a lot of diamonds did come from Africa. And before that, a lot of diamonds came from Brazil. And before that, a lot of diamonds came from India and historic mine workings on the island of Borneo as well. But this map here shows a lot of, well, it shows lots and lots of diamond mines around the world. I've got another slide where actually some of these numbers you can actually read on this little legend here, what these localities are. But for instance, Canada producing almost a quarter of the world's diamonds. It's got these primary diamond deposits, so they're mining kimberlites, mostly up here at the number 1. And this is the Slave Craton, where we've got lots of large diamond deposits in these kimberlite fields, these clusters up here. And in Russia, you know, over here on the right portion, we've got sort of 2 regions where they have lots of, again, kimberlites that they're mining. I think some people might have heard of Argyle in the news recently. And Argyle is a huge mine in Australia, and it is actually going out of production. Oh, I skipped ahead there by accident. It's pretty much done mining now. And so that's sort of a large portion of the world's diamonds that's been exhausted now. But the reason it's been in the news is because the Argyle mine is producing about 90% of the world's pink diamonds. So now that that mine is closing, the pink diamond market is going to be a lot smaller than it has been over the past almost 30, 40 years.
I think when the, am I on or not? I can't tell.
You're on.
Okay. I think the Argyle story was kind of interesting because the Australian government were quite sly when they did their initial negotiations with De Beers. They wanted to maintain control. And at that time, the big mines in Australia represented potentially 1/3 of the world production. And so they bought 90-something%, I think, or more of the production, which tended to be mostly industrial, with a very small percentage of gem grade. And then they knew they had Argyle sitting in the back, but it was inaccessible, virtually inaccessible. So they took the monies that De Beers paid them for the general production of the main mine, and they used it to build the road and to evolve and develop the Argyle mine, which was a high percentage gem quality and a very high percentage colored gems. And I think that was one of the smartest governmental moves in the world in terms of working with De Beers to try and maximize their yield from their own resources, because De Beers tended to dominate and control.
Yeah, very much so.
So what about these other newer mines that the Canadian have been? I know I don't want to see the stones quite yet, but we've been hearing reports from Africa where Canadian mining companies have been doing some interesting things.
Okay, yeah. So if you're talking about Lucara, I think.
Yep.
Yeah, Lucara is a Canadian company headquartered in Vancouver, and they've been in the news a few times in the past few years for their mine in Botswana, the Karowe mine. It's actually not numbered on here, but it's in Botswana here. And the big diamond that made headlines was this one a few years ago. They named it Lesedi Lerona, which means our light. And in some news headlines, it was listed as 1,101 carats. And that was later revised to 1,109 carats, which is maybe a little bit less satisfying than 1111, but it's a huge diamond. I think some people compared its size to a tennis ball, but this is just one of several large, high-quality diamonds that have come out of the Karowe mine in the past few years. So it's an exciting place. I mean, especially since prior to this, you know, people thought of a lot of these large, high-quality diamonds as coming from some of the key mines in South Africa, farther to the south, and also the Cullinan diamond, for instance, that came out of the Cullinan mine. Used to be called the Premier mine. Or no, it's called the Cullinan mine now. They changed the name, but this other diamond here. So this is a 910 carat diamond. It's found a couple years ago at the Lesotho Letseng mine. So Lesotho is a small country in Southern Africa. And, you know, this is another one of these mines that's been producing some of these very large, very high quality diamonds that are quite often type 2A, so they don't have any detectable nitrogen in them. And I've been studying these diamonds a lot for their geological implications. It turns out that a lot of these larger, high quality diamonds actually form in a different way compared to some other diamonds of smaller sizes and different colors. And so these ones seem to be distinct in a genetic sense. But we can go back to that map.
Can I ask you a question, if I may?
Yeah.
I'm puzzled actually as to what's happening differently in these particular African mines that are allowing the finding of larger diamonds, because most of the diamond processes in the mining around the world I've seen anyway crush things almost to oblivion, and so large stones don't usually make it through their shakers. So are they mining it in a different way to try and capture larger diamonds, or is this just luck?
Yeah, I mean, in the case of the Karowe mine, the answer is yes. They're having to pay special attention to how they crush it in order to recover larger diamonds. So they had to make a change to the way they process their ore. After they started the initial production from that mine, they realized they were recovering larger stones than they expected, and they put in an extra circuit for mega diamond recovery, where they don't crush it quite so fine and give themselves a chance to recover some of those larger diamonds before they get crushed down to oblivion, like you said. And that the Lesedi Lerona diamond, this one, you know, that was recovered very shortly after they implemented this new circuit that recovers the mega-sized diamonds. But at a lot of other mines, yeah, they're probably crushing to finer sizes because they're not expecting to find particularly large diamonds like this. There's sort of some sense of kind of risk management that goes in. You need to have an idea of what the largest diamonds you're probably going to recover are, because you can't crush everything to very coarse sizes and process it, because that's an added cost in mining. If you don't expect to find large diamonds, then you're not going to take that extra care.
I think the story was that only half of the colon really was found. The rest had already been lost in the mining process, and it was in the wall.
Yeah, I've heard that too. And I think someone even took the Cullinan rough and tried to recreate an octahedral crystal shape out of it using plaster to try to build it out, or clay to try to make this larger diamond and estimate how big it might have been. But I don't think they found any other large stones that they thought kind of fit together with it very well. But, you know, that was at a time when they were recovering a lot more things by hand. Now there's a lot more machinery involved. For instance, for the Lesedi Lerona, I mean, it's not really handled by humans until later in the operation. You pick it up and go, oh, look what we found.
Thanks very much, Evan.
No problem.
Kerry had a question. I don't know, Kerry, if you want to unmute yourself and say it.
Yeah, sure. Evan, I was just looking at your map there before, where you had the cratons and you've got your little blue lines, and it looks like where you've got blue lines going from, my geography is awful, looks like Greenland, that maybe that those go over to the north of Scotland. Do you think that there's any chance that they might find diamonds in Scotland, maybe on the Isle of Lewis where they have sapphires? Does the geology lend itself to a potential find there?
You know, I had never really thought about that, but if there are remnants of this older, thicker parts of continents there, then in theory, yeah, I mean, that's sort of the environment we usually think of in terms of diamond exploration. To my knowledge, though, I don't think there is any active diamond exploration there, and I don't think there have been any indications that there might be a diamond deposit there.
There might be explorations. Do you want to go on a trip, Jolien, and we'll go with some hammers and look for some?
Sure. Yeah, why not?
I think it would be fair to say that there are roughly how many major producing mines now in the world for diamonds?
I don't know if I have a good number for that. Did someone else have a good number?
I mean, and there is one special mine that I wanted to bring forward, and that's the only diamond mine in the world that I'm aware of where the public can mine for diamonds. Do you want to touch on that?
I think you're talking about like close to number 5 here, like in Arkansas, the crater.
Crater of Diamonds, Murfreesboro.
Yeah. Yeah, no, I've never actually been. I mean, has anybody here actually been there?
Roger has.
Yeah, I've been there
Long, long time
twice,
ago I was
but
there.
I did not find anything.
Yeah, I
I've
think,
been there 3 times, and I did not find any diamonds. I found a couple of garnets and some agate and jasper, which who knows if that was even part of the deposit originally, maybe the garnet. But it's was interesting, and people that live there find them. I mean, it's I wish I was there today. We just had gully washers, and this would be the ideal day to be out there right after the rain stopped. That's when you find them.
There was a fantastic fraud going on a few years back, about 10 years ago, which you may have heard of, that a local guy there was had an extraordinary run of luck finding diamonds at this mine and getting them all certified. And turns out that he had bought these diamonds on eBay from India, and these were all Indian diamonds which he'd smuggled in his pocket, and then fortuitously had just found in various places. So over the course of a few weeks, he found half a dozen or more of these fairly significant diamonds, which of course he could then sell as a premium for being US Arkansas diamonds.
yeah.
Fortunately, he was caught out by some clever internet sleuthing by people who managed to find the original eBay adverts showing exactly the same stones from India. But yeah, that happened.
Before
That
we
darn
leave,
internet.
go ahead.
I was going to say that darn internet again.
Yes.
No, I was going to say I've been there one time and didn't find any diamonds there. Found a really nice pyro up there though. Darn it.
Yeah.
But there was another guy maybe 200 feet away from us out there on that field that did find the real tiny diamond that day.
Well, I think that when they first were opening up the mines in South Africa, one of the side products of it were the so-called Transvaal rubies, which were garnets that are part of the normal mineralogical assemblage of a pipe. But just before we leave mines, Evan, could you just touch briefly on what the difference is between a barren pipe and a diamond pipe, and in particular, why do we have a pipe that has only graphite in it, which obviously is the other form of carbon, and it obviously came up from below, and something happened differently between when it started and when it ended, and with it either allowed it to be a diamond or graphite.
Yeah. So, I mean, I'm not aware of any pipes per se that have a lot of crystals in them that look like they were a diamond that has been turned to graphite. Although there are some deposits around the world where you can see an octahedral crystal that looks like it was a diamond and it's been turned to graphite. But those are ophiolites, where the diamonds have sort of been brought from mantle depth tectonically up to surface. But in terms of kimberlites, yeah, some kimberlites have many carats per ton or per 100 ton, and some kimberlites don't seem to have any. Maybe they have a few, but they're certainly not economic. And the ratio is somewhere around 1 to 100. So you might have to be doing a lot of exploration, finding kimberlite pipe after kimberlite pipe before you can find one that has an economic quantity of diamonds. And I think there are two major reasons why some might not contain diamonds. One is that they've erupted through a package of mantle rocks that simply doesn't have that many diamonds in it. Or the second reason could be that on their way to surface, the sort of chemical dissolution, or we call resorption, of the diamonds can essentially turn the diamonds into CO2 or dissolve them away until they're nothing. And some diamonds, some kimberlites have these diamonds that look like they're very, very strongly resorbed, and some of the diamond material is missing. It's sort of been lost. So it's very uncommon to find diamonds that haven't seen any resorption at all. So it seems like all diamonds around the world are affected to some degree by this process of being dissolved in the kimberlite melt as they're coming to surface.
What is considered to be an economic percentage per ton of diamonds to make a kimberlite worth mining?
Well, it can vary. I think people often talk of grades in the range of 1 carat per 100 ton to 1 carat per ton. But beyond that, a lot of the value has to do with the diamonds themselves. Some mines have a lot of diamonds, but the diamonds themselves are heavily included or gray and would be considered industrial quality. So the actual value of the diamonds doesn't always correlate directly with the grade in the pipe. And the other thing that has a big bearing on the value of a deposit, whether or not it's economical, can be the location. If you've got a fantastic deposit, but it's in a remote, northern location. For instance, there are some diamond deposits on Baffin Island or Victoria Island in the Canadian Arctic. This is suddenly very challenging to access if you wanted to turn that into a commercial production. It just makes the costs go up and up. So there's a lot of sort of complex variables at play.
Well, I think that's interesting because I think this is the tiniest amount of product per ton to make a mine feasible of any known mineral on the planet. The last question, this is the last question regarding mining, and I'm hoping it's of interest to people, is do you have any information as to why in Brazil we had so much carbonado as versus real diamonds? I mean, versus usable diamonds, which ended up being the original, diamond mining and mining drill bit diamonds because they were so amorphous and lacking real crystalline directions. What was the difference in the formation? Does anybody know?
Yeah, carbonado is a really fascinating material. For anyone who's not familiar, carbonado is like this polycrystalline, usually black kind of diamond. And because it's polycrystalline and the crystals are very, very small, all in different orientations, it makes it very excellent as an abrasive material. And before we were able to produce industrial quality diamonds synthetically, carbonado was like the primo kind of industrial quality diamond because it's more resistant to cleaving because it has all these tiny crystals in different orientations. So it's very wear resistant. But the way it forms in nature is not really known. It's unusual because true carbonado, not just any gray polycrystalline diamond, but true carbonado, what I think carbonado experts would call true carbonado, comes from Brazil. And we don't know exactly how it forms, but my favorite theory, which is open for investigation, is that it actually is from outer space, that there was some kind of a meteorite, not that it formed during an impact, not impact diamonds, but that it formed before our solar system, and that this is some kind of a diamond from space that has fallen to Earth and fragmented apart, and that's why we find it around in Brazil. And importantly, we don't find great examples of it in a primary volcanic deposit. It seems to be found in these secondary deposits. So it's just kind of a mystery.
Well, thank you for trying to explain it. Can we go back to the sharing of the main screen programming? outline, if you don't mind?
Yes, how do I now?
Oh, no, Jolan
Yep.
will take care of it.
Okay,
We've done that.
That was very interesting. Thank you very much for that contribution.
you're welcome.
Okay, Ray, back to you.
Can we go back to the outline, please?
Oh, to the outline. Okay,
Yes.
bear with me a moment.
Yeah.
And
We did wander a little bit there, but by the way, those diamonds in the background are from the Argyle.
Mhm.
Okay, so cutting. I'm going to skip that right now and get back to that if that's okay with you, Evan, because we've given you a fair amount of airtime there. Sally, is it possible you could talk to us about the variety of colors that naturally occur in diamonds and what treatments are done to make diamonds colored, and also what treatments are done to make diamonds more, or to appear to be more perfect?
Yes, of course. And I can also share my screen if that's possible.
bear with me a second. Of course it is. Right, you should now have the power.
Okay. Um,
And just to let everybody know that questions are welcome at any point in this. So don't be shy, please. I don't want to be the only one asking questions.
Along those lines, Ray, how do we ask questions?
You can send it on the chat. I'd like to ask a question about this, and then Jolan will bring you forward.
okay. Well, I'm going to go through all of the colors of the rainbow, and then I'll finish up with colorless diamonds. One thing that at the beginning, Ray was talking about a lot of the interesting aspects of diamond, and diamond is different from so many other different gemstones. Another reason I thought of when he was going through the list was I think diamond is the only gemstone that is valuable both in its very colorless form and also in its very colored form. Most gemstones like emerald, ruby, sapphire, they're only valuable in their colored form. A colorless sapphire would not have the same value that a colorless diamond does. And I'm going to go through some of the fancy colors first. By and large, the most common are yellow diamonds. About 70% of fancy colored diamonds are yellow, and about the vast majority of those are ones that are colored by what we call a Cape defect. And when I say, first got its name from the Cape in South Africa, but Cape now doesn't refer to that geographical distinction, but just any diamond that shows these peaks that are called N2, which is at 478 nanometers, and N3, which is at 415 nanometers. And just a couple of things I want to mention about these. This N3 peak is also what causes blue fluorescence in any diamonds that do show blue fluorescence. By and large, that is due to emission by this N3 peak. And also the N that we see here, that doesn't mean natural. That doesn't mean nitrogen, it means natural. These were named decades ago before they were identified, and they just counted peaks across the spectrum and said N1, N2, N3, and so on. And so that's how these got their names, where this N stands for natural, not nitrogen. It just happens to have nitrogen in it. And then there's a couple of other ways we get yellow color in diamond. Another way is type 1B diamonds. That's where you have single nitrogen. At the beginning, Evan was talking about diamond type and talking about how diamonds that have nitrogen go through this aggregation process deep in the earth, where very young diamonds start off with all of the nitrogen as single isolated, all of the nitrogens are off by themselves. And then over time, all of those nitrogens will sort of find each other and pair up. And then once they find each other, they want to stay together. But if they haven't paired up yet, then they're still isolated in type 1B. And that gives a very pronounced yellow color to diamonds. So actually all new diamonds that have nitrogen, when they're very young in the earth, they start off as this very yellow color. And it's that aggregation process where the nitrogens pair up that causes them to decolorize into the colorless that we see so often today. And then there's a couple more diamonds that we see that have yellow color. And not all of these are as common as those that are colored by the Cape defects or the single nitrogen. And those are diamonds that have a 480 nanometer band, for instance. And this is one of the mysteries that we still have in color science, is that we don't really know what causes this. And so we're still trying to research what are the atoms, what are the defect configurations that are causing that. Pink diamond, the vast majority of them, about 99.5% of natural pink diamonds, get their color from this plastic deformation where they're deep in the earth and they undergo stress, and that causes the atoms to slip next to each other. And that's the majority of the pinks that we see, the ones that are from Argyle, the ones that we see from the Siberia mines. All of those have that 550 have an absorption band centered about 550 nanometers that gives this pink to red color. Very small percent of diamonds are called Golconda pinks, where they get their color from this nitrogen vacancy centers. The vast majority of green diamonds are due to irradiation, and that's natural irradiation within the earth, due to being in physical contact with radioactive fluids or a radioactive mineral grain. And that's also one of the big issues we have right now with diamonds, is trying to distinguish natural irradiation from laboratory irradiation, because once we see the spectrum, it looks very similar to between natural and irradiated diamonds. So we have to look at many different aspects and use other different tests to try to distinguish out what's a natural irradiation and what's lab radiation. So that's one of the big challenges we still have. And people have been trying to determine that for decades, and it's still an issue today. And so there's definitely more often than we would like, if someone submits a green diamond to us that we may not be able to determine the cause of color, it would need to have an undetermined color origin. And that probably happens more for green diamonds than any other color class of stone. Among blue diamonds, you normally think of diamonds that are colored by boron, such as the Hope diamond. And about 1/3 of blue diamonds are colored by that. Another third are colored by what we call hydrogen defects. And we're not fully sure what is happening within these diamonds that gives rise to these bands, but these are predominantly from Argyle mine. And so it'll be interesting to see what happens after the Argyle mine closes and we no longer see this steady supply of these diamonds. Another major cause of blue diamonds are those that are colored by irradiation, but instead of the green diamonds, these don't have absorption in the blue due to nitrogen defects. They just have, these are more often type 2A, and so that shifts the color window from the green into the blue. We talked earlier about the Hope diamond, and that's one of the most, and the phosphorescence of it is one of the is a famous aspect that we see in it. And actually all type 2B diamonds, or almost all type 2B diamonds, do show some observable phosphorescence. And the phosphorescence that we do see is either at a phosphorescence band that's centered at 660 nanometers that gives a red color, or it's a phosphorescence band at about 500 nanometers that gives a blue color. And sometimes we can see a combination of them both. For example, if you see the Hope diamond phosphorescing in light, you can see it starts off as an orangey red color, and then it gradually morphs into a pure red color. And that's because that blue band is there simultaneous with the red phosphorescence, and then the blue decays away, leaving only the red. That's how we're able to see both colors within the phosphorescence of the Hope diamond. One interesting thing about the blue diamonds, or blue to gray to violet diamonds that come out of Argyle, is that they have this slight Alexandrite effect, where they will look blue or bluish gray in daylight, and so that will be the color grade that they get on the report. And then if you look at them under incandescent light, they appear more violet. And so you can get this sometimes this very pronounced and beautiful color shift between daylight and incandescent light for these. And again, we've only seen these in diamonds that are from Argyle. And then this is a very minor class of stones, those that are fancy white or fancy black. And these have color that are generally due to nanometer to micrometer sized inclusions. And and so you can, with these, you don't really see a difference in color saturation or vibrancy. Instead, you see a color difference in how translucent to opaque these stones are. In terms of treatment, what we see mostly there's 3 different types of treatments that are possible. One is just HPHT processing, and that can be done on several different types of diamond, depending on what you want the final color to be. If you're looking at, say, a brown type 2A diamond, then you are able to expose that to HPHT processing and decolorize the diamond. You're able to take the brown color out. However, if you did that to a type 1 diamond that had quite a bit of A aggregates in it, you did that same HPHT processing, you'd come up with this very vivid yellow. So when Evan talked a lot about diamond type at the beginning, something really important that we do is one of the first tests that we run, just because we know what would be possible for a diamond to undergo and what the ultimate color could be after treatment. And so, in order to decolorize a stone, the only possible treatment really is to perform HPHT treatment on it. And there's only a very small percentage of natural diamonds that can undergo that treatment. The vast majority of natural diamonds, about 99% of natural diamonds that are in the D to Z color range, cannot be treated to decolorize. So if we take a spectrum on a type 1A diamond and we see that it's type 1A and it's, say, a G color, then we know just immediately that it is a natural color and it is a natural diamond. If it's a type 2 diamond and it's, say, a G color, then we need to run more tests on it. If we're looking at fancy color, there's a number of more treatments you can do. You can do HPHT processing in order to impart yellow color into a diamond that has nitrogen. You can irradiate a diamond to give it a green to blue color, or you can do this combination of treatments. One that's most commonly done is where you get different treatments. You do first HPHT treatment, and then an irradiation, and then finally an annealing. And that's how we often get pink color in diamonds. What the HPHT processing does is that it creates single nitrogen, and then what the irradiation does is it creates vacancies. So you've got nitrogen, you have vacancies, and then you need some low temperature annealing to put them together and create these nitrogen vacancy centers that give a pink color. So I sort of gone through very quickly about some of the natural colors in diamond and some of the treatments that we see often. And I hope that is a good introduction to color in diamond.
Well, thank you very much. And one other question in terms of treatments. I know that obviously one of the big C's in diamonds is clarity. And
Yes.
so there have been tricks that have been using lasers and infilling. Could you talk about that, please?
About clarity treatments? Yeah, there's a number of different possibilities with laser drilling and with internal laser drilling. But with those, there's a good gemologist will be able to find those telltale signs of the drilling and the clarity enhancements. So it's something that I don't think we see too often, but it's only out there and is available in the trade.
Well, thank you very much.
Eloise, did you want to add something?
Thank you, Sally. That was a great introduction to a complex story here, so that you did a wonderful job at doing that. Of course, you know that I will ask you a question about pink diamonds. I saw that you had a little diagram showing the twinning, and in between the twinning you had some cluster of vacancies. Can you tell us more about that? Is that something that you took from previous research, or that's something that you're working on and that you discovered recently?
That's just from previous research. We're still trying to determine everything that's going on inside the pink diamonds, and it's definitely been something that I've been wanting to know more about for a couple of years. But we're chipping away at it slowly, but we haven't made any major breakthroughs as of yet.
Thanks. Keep on doing this great job. Thank you very much, Sally.
Thank you. Just one quick question at the end here of this section is, when I was younger, and I'm old, but when I was younger, one of the things that they used to try and promote a really nice diamond, it was a blue-white diamond. And we found out later that this was really a byproduct of fluorescence, which now is not considered to be a plus. So could you just explain why the blue in the blue-white fluorescence is now considered not to be an advantage? Sorry, I didn't mean to throw you a curve.
Oh, no, that's quite all right. There is some issue that has been built up in the trade about blue fluorescence, and how much of it is substantiated by what people see and how much is just what's been built up in the trade. It's a little difficult to try to deconvolve those. I think a lot of people, if they are looking for a good deal in the diamond world, they go for something that has strong fluorescence or medium to strong, because they know they can get a good deal due to a price lowering due to the fluorescence. I don't think that there's I know for some diamonds, if they have a very, very strong fluorescence, it's sometimes conflated with it looking very, having an oily appearance, and how much we see that due to the fluorescence and how much is due to other things that are involved in the diamond. For example, I was showing earlier type 1AB diamonds that I was talking earlier about fancy white diamonds, and by and large, those are type 1AB. And type 1AB diamonds often will show some more what we call milkiness, and oftentimes those also have some very strong fluorescence. And so whether we're looking at two different observations and trying to combine them together, and whether they are independent or whether they are dependent, it's still a matter for debate. But I have some of my colleagues here at GI have done quite a bit of research on fluorescence, and I think they're going to be publishing some good research on that in the coming months.
I'll look forward to that. Thank you very much. Are there any other questions that come out before we leave this particular section? I was going to suggest that we have a 5-minute body break, and those who are wanting to come back and talk about some of these other subjects, I'd like to continue if that's okay with the consensus.
Sure.
Is everybody okay with that?
Sure.
So if you want to blank your screens or whatever, and do what you need to do for 5 minutes, and come on back, and we'll carry on.
I'll put the this up in the meantime.
Thank you very much. Are we back?
Sure.
All right.
Okay.
We wanted to get back to, I mean, one of the mysteries of diamonds, as far as I'm concerned, is the fact that it comes in a relatively uninteresting chunk of stone when it starts off, and through the science and technology of cutting, we move that into something that is capable of wowing us in terms of refraction and colors. And so Evan had volunteered to talk a little bit about the process, and don't want to be too technical. If you could just give us an idea of the processes and how it's changed. It used to be, you saw the pictures of the man that was sweating bullets with a cleaver trying to cleave the massive diamond before they cut it. And now, of course, we use lasers for that. But I'd like you to talk about a little bit about the process, because I think this is a mystery to most people, and it is different in many ways from standard faceting that we use for other gems. Evan.
Yeah, very much so. Would I be able to share a couple slides?
That's up to Julian.
Sorry, yes, you have control over that.
I have the power in my hands already. Yeah, okay. So can you see this slide now?
Yeah.
Okay, so I would sort of divide up this sort of idea of going from a rough crystal to a faceted gem diamond that we're more familiar with into a few different stages. So a couple of the initial stages would be just sort of giving the diamond some kind of a shape. And that is like what you just said with the guy sweating bullets. There's that famous image of, I think, Joseph Astor trying to cleave the Cullinan diamond. And, you know, he's got this mallet up in the air. He's about to come give this little knife a big whack and sort of hopefully split the diamond apart on a cleavage plane. So the diamond is very, very hard, but it cleaves almost perfectly along the 111 or the octahedral plane. So that's one way of sort of dividing up crystal into smaller fragments. The other method would be to saw the diamond and then sort of giving it a round outline, for instance, for a round brilliant, that's sort of shaping it further. Traditionally, that's been called bruting. And the last part, actually putting polished mirror-like facets on it, is polishing. And that, like you said, is very different from the way we polish other materials. So this is sort of what it looks like, the key equipment for polishing diamonds. And this has remained virtually unchanged for hundreds of years. And the idea is that you've got the diamond, and the diamond would be held here. And this is sort of cemented in place into a little brass cup here, but it could also be held in place mechanically. And this thing that kind of holds the diamonds, this is called the dop, and it's fixed into this piece that you hold on to called a tang. And so the diamond is sort of held securely in place, and then you bring it into contact with this rapidly spinning wheel here, which is called a scaphe, and it's rotating at about 2,500 to 3,000 RPM. So at the outer edge of this scaphe, it's moving past the diamond at almost 30 or 40, 50 meters per second. So it's pretty fast. And the really interesting thing about this is that it's not really abrasive action that's wearing the diamond away. So most other forms of polishing, for instance, like if you've ever polished a thin section, or if you've polished other gemstones, you think of it usually as a harder grit polishing away or scratching away a softer workpiece, the gem that you're faceting. But in the case of diamond, there isn't anything harder, and you're actually polishing the diamond with small particles of diamond. So this scaphe has this very, very small particles, like micron size or 10 micron size diamond grit embedded in it. But at the actual interface where those diamond particles are sliding up against the diamond, it's not actually scratching away pieces of diamond. There's something more complex happening there that we actually don't understand in complete detail, but the diamond that's being polished away is undergoing some kind of a phase transition. So the carbon bonds are changing a bit from being sp3 hybridized to being sp2 hybridized. So it's almost like it's not diamond particles breaking off or being scratched away. It's actually changing into another form of carbon right at that interface. So this is a skill unto itself. It's hard to master, but it's a lot of fun. I've had the pleasure of doing some diamond polishing myself, not to make faceted gemstones, but to polish down to inclusions and expose inclusions so that we can examine them in more detail to learn about their chemistry or you know, other things like that. But diamond polishing is really fascinating, in my opinion. I can also show you what sawing looks like. I think I've got a couple of slides in here. This is traditional sawing that's been around for just over 100 years. So instead of breaking the diamond apart, now you want to do it in a very controlled way. So this is what the saw looks like. It's a slow and steady process. You've got this rotating disc that's bronze, and again, it's got diamond particles in it. And it's kind of similar to what's happening during the polishing process, except this is happening just along a narrow little line, and you can slowly kind of wear away the diamond and like cut a little slot right through it. But now most more controlled or higher value stones, the cutting is achieved with lasers. And this is a neat image I like, showing one of these laser cutters. And this is a famous diamond from a few years ago that was cut. And this is the first cut that was made. They kind of nicked the end off here to facet one gemstone out of this piece, and then the rest of it will be cut up further into smaller gemstones. I think that's all I wanted to talk about it for cutting and polishing.
Well, I just wanted to, if you'd bring forward the advantages, for example, of the princess cut, or I think that's the one that's got the triangular edges and the brilliant bottom, which takes advantage of the least amount, because this is a very wasteful cut when you do a brilliant cut.
Yeah. If we go back here, I mean, this second image here, right after sawing, we've taken this, a lot of diamonds have this primary shape of an octahedron, and if you sort of lop the top off, you make something with a kind of square outline and a pointed bottom. And if you add some more facets onto that, that's essentially what the princess cut is, where you would be losing very little material. If you actually want to round off the corners and turn this into a round brilliant, you lose more weight in the diamond. So the princess cut is sort of that, yeah, making most use of the octahedron.
Total internal reflection?
Yeah, I mean, that's sort of what you're trying to achieve with the optimal facet angles in the pavilion. You don't want the cut to be too shallow or too deep, or else you have light that isn't coming in, bouncing internally and coming back out the way you want it to. So the angle of the pavilion controls that, just as like it controls that in any gem material. But diamond, because it has a fairly high index of refraction, it does have total internal reflection a little bit easier than some other gem materials.
Okay, while we have you on screen, I know one of your pet interests is inclusions, because they allow diamonds to tell a story. Could you just quickly, without being overly technical, share a little bit about that?
Yeah, I mean, I think I have a slide I can pull up that might show a couple inclusions here. How about this one? So here are a couple examples of some pretty common inclusions that we see in diamonds. And all an inclusion is, in the diamond, as it's growing, sometimes it will envelop some surrounding mineral grain. and it becomes trapped in the diamond, and it's another foreign mineral trapped inside the diamond. And so, for instance, if the diamond is growing in a peridotite host rock, it's quite often the case that a little olivine crystal might be trapped in that diamond. And the reason this is really interesting from a geological perspective is that this inclusion, once it's trapped inside the diamond, it's very well protected because diamond is almost like chemically inert, and it's very, very strong and resistant to fracturing or just breaking apart. So the inclusion stays very well protected on its way to surface. And now we can see the diamond that has grown in a place that we can't access in any other way. And it contains a little snapshot, a little physical sample of that environment. So this olivine might have been trapped at 200 kilometers down in the earth, and it might have actually been trapped a couple billion years ago. So it gives us a way to study the interior of the earth that no other material available at the Earth's surface can do. So diamonds are really special for Earth science in that way. Here are a few more inclusions that are also interesting. These ones actually were trapped much deeper in the Earth. So these inclusions were probably trapped down close to the boundary between the upper mantle and the lower mantle, right around 500 or 600 kilometers deep. So sometimes we get an extraordinary look to unbelievable depths inside the Earth just by looking at the inclusions trapped in diamonds. And if it weren't for diamonds' popularity as a gem material, we wouldn't be recovering this stuff, and we wouldn't have inclusions to look at. So it's kind of interesting to me that there's this symbiosis between the beauty of it as a gem material and the value of this as a scientific kind of insight.
Are there any questions? I think there's an irony here, Evan, that you find this of educational value, whereas most people who own diamonds find this as a detriment. Oh my goodness, there's an inclusion in my diamond. It's not as good as somebody else's. So, I mean, obviously this is a complete turn or 180-degree turn looking at inclusions, because most times they're looked at, I think, as a negative in terms of clarity in a diamond.
Yeah, absolutely.
So it's nice to have a fresh look at what's considered to be a bad thing.
Yeah.
I do have a question.
Go for it.
Okay.
Go for it.
Skipping back to the laser cutting,
Yeah.
how does that work? Is it literally igniting the carbon and cutting through it, or is it something else that causes it to cut so cleanly?
Yeah, no,
Thanks.
the laser is very tightly focused to a very small spot, and the diamond is very locally heating up to a point where it essentially vaporizes. The diamond is being ablated just in that one little spot. And then the diamond, its position relative to the laser is controlled with a computer, and it's sort of motorized on this little stage. So it can be manipulated very exactingly to sort of control where that ablation is taking place, so they can sort of move the diamond back and forth and saw through it. But you can also trace other paths and make like a curved cut, or make a partial cut and then another cut. They call that pie cutting. You like cut out a wedge from the diamond. But it really is the diamond being sort of ablated, or just heated up to the point where it's no longer stable. But the diamond immediately adjacent to that is fine. It's not harmed in any way. It really doesn't experience the same heat at all, just because the laser energy is so tightly focused.
Thank you. That's exactly what I wanted to know.
You're welcome.
Thank you.
When you showed the image, though, the cut face was black, so we're assuming that is it's a pure black carbon side effect of being burned.
Yes, that black color is either you would consider it graphite or graphitic, or just non-diamond carbon. So it's right on that interface, it's been turned black, and you have this thin layer where it's not really technically diamond anymore. But that can usually be polished away with minimal loss, and then you still have a nice diamond right underneath that.
Because of its thermal conductivity, it doesn't have any shock damage value at the site.
Yeah, exactly. A lot of the heat, localized heat, disperses very quickly through the crystal structure, exactly for the reason that you said, that it has a very high thermal conductivity.
Now, can we get back to Sally for a minute, please? Sally, the question was, we all, in the trade anyway, have gadgets that help us identify stones in people's jewelry, whether it's a diamond or whether it's a substitute, a fake. And I think these tools use the heat and electrical conductivity properties of the diamond. Could you just explain that very briefly to people? Because I know I spent good money on these stupid tools, and they do work.
I think you're talking about thermal conductivity testers, and those will work to distinguish diamond from most of the other simulants, such as cubic zirconia or but one place where it will not work quite so well is trying to distinguish diamond from moissanite, as moissanite has a thermal conductivity very similar to that of diamond. And so the thermal conductivity testers just are not sensitive enough to distinguish silicon carbide in many cases. And but it can work for many other simulants. There's also a number of testing instruments that are on the market to distinguish, to try to distinguish natural diamond from laboratory grown diamond. But some of those instruments do not distinguish simulants from natural and lab grown. And so there are some simulants that may pass on one of these testing instruments, even if it's cubic zirconia. So it's just good to know with any testing instrument what it is that it's measuring and what, say, a pass means. Does the pass mean it's natural diamond, or does a pass mean it's not lab-grown diamond? But it doesn't preclude the chance that it's a simulant.
So there's no quick and easy way of telling when you're looking at a diamond whether it's been synthetically colored or naturally colored.
Or grown.
Or grown.
Yeah.
Oh, that makes it so dangerous out there.
I wish
you really
that were
have
the
to
case.
trust your diamond dealer.
Yeah, yeah. I wish that were the case. There are, I mean, many of these instruments will be able to distinguish that vast population of natural diamonds that have nitrogen, and those can be certified as natural color and natural origin. But those that refer, you would have to do more testing, and it's not definitive on those.
Oh, thank you very much. So you also said you would help us with historic or good stories about diamonds, and you had, I think, some up your sleeve of diamond stories, because diamonds are interesting more than just all the technical things we talked about. There's an awful, I mean, they've been deeply involved in politics and wars and all kinds of things in the world's history to this date. And I'm hoping we can share before we close not only some stories, but some images of interesting diamonds and some interesting stories.
Okay. Well, the most interesting story I have about a diamond is actually the first diamond that I really studied as part of as looking at gem diamonds. My background before that was growing CVD synthetic diamonds for engineering applications, and I was working at the Naval Research Lab in Washington, D.C., and I started doing a collaboration with the Smithsonian, and started looking at the phosphorescence properties of the Hope diamond and other blue diamonds in their collection. So that was my first exposure to any gem diamonds, and I got to start with the best, or with the Hope diamond. And so that was such a great experience for me. And I know Eloise has also got a lot of great stories about the Hope diamond. I'm sure Scott does as well. And so just getting to be up close and personal with the Hope Diamond was and didn't have to have just getting to intersect with the Hope Diamond. It was amazing history. It was a really great experience for me.
And no bad luck rubbed off on you.
No, it was no. I was actually pregnant with my second child at the time too, and no bad luck on him either.
Thank you. That's a good segue for Eloise. Eloise, are you willing and ready to share with us?
Hello there. Yes, sure. I mean, you know, like now I work for the School of Mines in Paris, so we don't have that many great cut diamonds. So I'm not going to tell you any great story about cut diamonds, but I wanted to share with you tonight, well, tonight, yes, sorry, it's 10:30 p.m. here, something about natural stone that we have that is still rough and still inside its Kimberlite host rock. Julian, do you mind if I can share something on my screen here?
Oh, bear with me a second.
Thank you.
You
You've seen already
should
plenty of
be
beautiful
good to
gem cut diamonds. I see some nice Argyle sweets on Julian's background right now. So
You should be okay to do it now.
Yes, I am. So this is the rock I wanted to share with you, and maybe I think that Evan would appreciate as well. Look at his face right now. I was like, yes, something rough that is not cut yet. So this is a stone from the School of Mines in Paris, and I really love it. It comes from South Africa, and it arrived in the collection at the very end of the 19th century, very much at the beginning of the mining of South African diamonds that were found in the primary rocks for the first time before the before 1860s. Basically, the diamonds were mined in the river as secondary deposits, but a big turn was made when we discovered the diamonds in the rough inside their host rock. So what you see around the diamond here is a kimberlite. This is a magma, the magma that brought the diamond back to the surface of the earth. So it's really, really important for us as geologists. So this little guy here is about 1.7 centimeters, 17 millimeters. So it's something, and it's not a small rock. I have a few other. So this is a close-up here. A few close-up. So this is the perfect shape of a natural diamond. This is what we call an octahedron. And the great thing about this specimen as well is that, unlike most specimens that you will find in museums, the diamond has not been glued back to the host rock. You will see a lot of museums you will visit. You will see just an octahedron and glued to the kimberlites. For one main reason is that this kimberlite, this magmatic rock here, is very fragile. It breaks off. It's kind of a breccia, this rock, so it's really easily torn apart. So it's still intact. This is one of the specimens that we will not move out of a museum. We loan a lot for various temporary exhibits all around the world, but this one will stay inside for the problem that the host rock is really fragile. So another view of the same diamond here, and I wanted to show you. Hopefully, it's going to arrive back. I really like this one. It's nicely contrasted here, and you see the trigone on the surface. So this is a natural etching figure here that you see on natural diamonds. And to make Evan happy, I want to make him happy here by showing him this. Little inclusion. So this one has everything for me as a geologist. It has the host rock, it has the kimberlite that brought the diamond back to the surface on like 150 kilometers deep inside the earth. It has the perfect octahedron shape. It has some nice clues to where it comes from and when it was formed, because I can't remember, I don't think that you mentioned that even, but you cannot date a diamond by looking at its isotope carbon content, because carbon isotopes fade very quickly for us geologists. They fade in tens of thousands of years, while diamonds mostly are 1 billion to 3.2 billion years old. So you will have to look at inclusions in diamonds. Again, you will have to break the diamond down if you want to know its true story. So yeah, that's what we do as geologists. We like breaking diamonds to know the story and to tell us what they reveal and where they come from, when they were formed. So this is the little guide that I wanted to share with you. I don't think I have any more other photos, but just a rough, just to change a bit.
Wow, thank you.
You're welcome.
I can imagine the excitement of the person who found the matrix specimen. But in the on your screen here, we have one person who is a field geologist who's did a lot of work up in the Arctic of Canada. And while he was doing work with drill cores and breaking them and doing recording, an amazing thing happened when he opened it up. Joran, can you tell us how many carats roughly the stone was? He opened it up and there was a beautiful diamond crystal right in the middle of the drill core.
Yeah, it was a 2 carat stone.
Whoa. Yeah, and just that is so rare. And I feel very honored because I managed a long time ago through Mindat, actually in a trade, to get a drill core from Mearpipe that has embedded in it a diamond crystal. So they're very, very rare to be found in drill cores. And so that's an experience that very few geologists that I know of have ever had. And I think it was a sort of a scary moment because you're not supposed to be touching diamonds when you're in the mining of diamonds area. So it's a very nervous, like it's like a hot potato. How soon can I get rid of this drill core?
Yeah.
And Goran's actually been in more than one field, I believe, in the diamond fields up in the Northwest Territory. So a man of interesting background. So anyway, anybody else have any diamond stories they'd like to share? And are you still with us, Mel? Oh, maybe not. At any rate, I wanted to thank every one of you, and particularly the people from GIA, Sally and Evan. Thank you for your contributions. And I really appreciate, Eloise, your contributions as well. And I'm hoping that as a group mind, we've learned some things that we may not have already known about diamonds. And I hope that also we've expanded our knowledge of this particular stone. So a question to the group, and please open your mics on this one, is when would you like, we're going to try and do this on a monthly basis. And so when would be a good time next month to have our next meeting? I proposed to Jolion that we might want to consider that space between Christmas and New Year's is to be fair game. And I'd like to hear back from people that are here as to whether or not that'd be something you'd like to do.
That's open for anything.
Yeah, anytime works.
Yeah, it's a lot of fun. I'd come back.
Well, I'm glad to hear that. Scott, did you have one of your famous diamond copies anywhere near you there?
Yeah, hang on just half a second. I can flash you a collection, I guess.
Yeah,
It'll just
Scott's
take me a minute to open it up.
faceted copies of almost all the famous diamonds, if not all of them. I don't know how many he has. So he has a bit of an interesting
I have
reputation.
42.
Only 42.
Only 42. All right, I'm going to try to get this on camera.
Wow.
Oh.
So he's faceted. Yeah.
Oh, that's incredible, Scott. That's wonderful.
Very nice.
Yeah,
Beautiful stones.
it's for the Briolette of India. I cut a replica for the GIA Museum in Mumbai. And I've just not gotten around to cutting one for my own collection because I don't have any Briolettes in my collection.
Well, that's a skill set that not a whole lot of cutters have. Thanks for sharing that.
Oh, my pleasure.
Thank you.
So the hope for stone next time was Opal. Is that okay with everybody?
Oh,
Absolutely.
yeah, my favorite.
Sure.
And if you have any experts that you would like to refer us to so we can contact them and invite them to be involved, it would be greatly appreciated. And I'd be remiss if I did not give kudos to Jolion, because I don't know if you all know him or of him, but Jolion is a gifted programmer who created probably the best, if not the best, gemologically oriented, freely available gem site, which is gemdat.org. And a recorded version of this program today will be stored and available on gemdat.org. So if you want to write down that name if you don't know it, that's a very important site. He also created the world's most visited and largest and most comprehensive mineral site, which is mindat.org. And so the world owes Jolion a great debt for making all the information available and making it possible for people to gather together and share ideas and share their love of minerals. And hopefully in the future, as we expand it, gemdat.org will make that a possibility as well. Whereas people of like mind who love gems and are curious and want more knowledge about gems and wish to find out and get help about gems, that they'll be able to do so through these organs. So thank you very much, Jolion, for making this site available and being here to work so hard to make it work tonight, because tech is extremely important for a program like this. Thank you all so much for giving of your time, and we'll look forward to seeing you again, and we'll try and get the word out to you all as to the exact date at the end of this year in December, when we will be having our next Opal meeting. And hopefully we'll have some good stories and some awesome information about opals to share and to discuss. And I'm hoping that as a group, we'll have just a teeny bit more discussion than we've had in terms of the general membership and attendance. Thank you all. And unless there's any other questions or information, perhaps it's time for us to bring it to a close.
Yeah, there was one more question in the chat. Woody has asked, how stable is the kimberlite? Does the blue ground go to yellow ground in museums?
I mean, for me, it just breaks apart because the kimberlite, depending on how the kimberlite is in the first place, it's not going to transform, but it's already really much a breccia. So it will decompose if you don't take care of it. You know, like this piece has been in the museums in the 1860s or 1870s. So you just have to be careful and just take care of it. But it's not going to change as it would change under the ground, if you want, for sure. So I had actually one question. Wait, can we actually share this group information to a wider community of gemologists? As I was asking you earlier, I know that the French Gemological Association would be happy to watch the series. So if we can share, it would be great to be able to share that.
It'll be available and archived on gemdat.org, this meeting, and as will all future meetings. And I'd really appreciate if you gave a personal invitation to the French Association. We were supposed to have attendance from the Spanish one, but apparently that didn't happen. So whatever the case, Canadian, GIA, and hopefully in the future, GEM-A will be involved as well. So we're hoping to hone in on the audience who really love gems and have a vested interest in knowing more.
I know this was also a little bit of a test run because this is the first one that we did. So although obviously we have tried and done a lot of hard work to promote this everywhere, we have obviously tried to keep this relatively small to start with, so that at least we know how it's all going to work and how we can manage it. And I think now we've got a lot more experience on this, and I think we will be able to cope next time with a larger crowd. And obviously everything that has been shared today will be shared online to a large audience anyway. So thank you all again for your fantastic contributions.
And thank you all.
Darn good for a test run is all I can say.
Yes, it went well.
It's only as good as the audience that contributes. Just saying. So if you guys like what you saw, please tell other people and get them involved so we can have a broader audience in the next run now that we've had our feet wet.
And if anyone's got any ideas for future episodes and what we should be discussing once we've done Opal, start thinking about it, because we've got a lot of gemstones to go through.
Yeah, and for those so-called gem nerds out there, we're hoping as we progress to also include occasionally some rare and wonderful stones, so that we can delve into those as well. So rather than just the traditional stones, I think the future does hold more interesting material.
Mhm.
And
Excellent.
since you mentioned it earlier, maybe when we do soft stones, I can show you my concave faceted sulfur.
Yeah, fantastic.
That would be
Another
wonderful.
element. The element is there.
Mm.
Well, thank you guys so much, and we'll hope you have a great month ahead and a nice Christmas. And we'll look forward. We'll get the word out as much as we can as to the date, so that we can get everybody a good chance to plan for it.
And thank you, Ray, for putting this all together.
Yeah, thanks,
Thank
Ray.
you.
Thanks, Olga.
Great. It was great.
Okay,
Thank you.
shall we call a close then?
Okay, thanks very much, Jolion.
Okay, thank you
Thanks,
all.
guys.
Great
Thanks,
experiment.
guys.
Or
Yep.
good afternoon, or however it is.
Likewise. Cheers.